In the following example, we will see how to model other type of physical processes using separable differential equation. Specifically, we will talk about one of the so-called mixing problems, which consists in determining the dynamics of the percentage of some quantity dissolved in a body of, say, water, which changes over time, and the problem involves some mixing. So what exactly we mean by mixing will be explained shortly. So let me outline to you what this problem is about. So here we have a tank which holds 5,000 liters of water. Here is our tank. It has 5,000 liters of liquid in it. Now, in addition to the tank, there is a pipe through which brine containing salt is entering this tank. Now, at the beginning, the tank contains 20 kilograms of salt. So first you have 20 kilograms of salt in there, and then there is flow of brine which goes into the tank. And this flow, the brine that flows in, it contains 30 grams of salt per 1 liter of the liquid, of the brine. And so we have 30 grams of salt per liter that flows in with the rate of 25 liters per minute. So that's the intake. Now, in addition to that, so we have tank, we have brine flowing in, and some initial mass of salt in the tank. Now, of course, the tank will eventually become full, and we need to drain it. So what occurs in the tank is there is some mixing. So as the brine flows in, it mixes fully with the brine that's already in the tank. And so full mixing means that the concentration of salt in any volume that you may draw from the tank is the same as it is in the entire tank. So say if the entire tank has mass of salt which constitutes, say, 1% of the total mass of the tank, of the liquid in the tank, then whatever volume of brine you may draw from the tank, say you take 5 liters from there, then it will be also 1% of these 5 liters mass-wise that is the salt dissolved in it. So this concentration is uniform throughout the volume. So that is what full mixing means. All right, so back to our tank. So as I explained already, because we have constant intake, there is also a drain that must be happening. So the tank is also draining after mixing, and it drains at the same rate, of course, because it has to maintain equilibrium. It drains at the same rate of 25 liters per minute. So the question we have to answer here is, what is going to be the mass of salt in 30 minutes after this process started? So we have at the beginning of the process, we have some mass, then we have this constant mixing and influx of brine and draining happening at the same time. What is the mass of salt dissolved in the tank in 30 minutes from the start of the process? So the idea here is that we want to model this situation as a differential equation for m of t, and this is the mass of salt in the tank. So we model this problem as differential equation for the mass of salt in the tank. Obviously, this function m of t evolves with time. T denotes the time variable. Let us think about what we can say about this quantity. So for the mass of salt in the tank, what are the factors that impact it? First of all, you have the influx of brine. What does that bring? Well, that brings us 30 grams per liter at 25 liters per minute. So every minute we get this mass per liter times this many liters per minute. So this is the influx of the mass of salt, and so this means I'm talking about the rate of change of the mass rather than mass itself. So as a function of time, dm over dt looks like this. So every minute I'm getting this fixed mass of salt. It is fixed because the brine has constant concentration. Okay, so this is the mass I'm getting in every minute. What is the mass that I'm losing? Well, obviously I'm losing because of the drainage, right? How do we determine how much salt I'm losing through that? Well, I will be losing 25 liters again. So I have 25 liters. And then I need to multiply 25 liters by the concentration of salt in that volume that I'm going to losing. So for brine, that was easy because we were given this concentration. Now for the solution that is being drained from the tank, the concentration is given by the ratio of the mass of salt in the tank to the mass of the entire tank. So as I explained to you previously, complete mixing in the tank means concentration of salt is constant throughout the tank. And so we just take the average concentration, which is mass of salt, divided by the total mass of the solution in the tank. All right, and so as a result, we get this relation, the relation between derivative of m with respect to time and m itself. So what we're going to do now is we'll simplify this equation and try to separate variables. So hopefully this is a separable differential equation, so we're going to be able to solve it. And here we have 5 times m divided by 1000, or equivalently I could write it for some more cancellation. I could say, well, this is going to be m over 200. Once I perform all the cancellation, this is what I see. After reducing to the common denominator, I have 75 over 100 minus m over 200. So I can write this as 150 minus m over 200, say. All right. Now, is this a separable differential equation? That's the main question to answer. Well, we see that in the right-hand side, we have a ratio of a term that depends only on m. This numerator only depends on m, and denominator depends only on t. So again, the denominator does not even depend on t, strictly speaking, because it's a constant quantity. So that is okay. We can still view it as a function of t. And so the separation of variables here takes the form dm over 150 minus m equals dt over 200. So this is great. We're going to be able to integrate this. If we integrate both sides, we'll get, in the left-hand side, we have minus logarithm of 150 minus m equals t over 200 plus a constant. So again, as we have seen previously, we have already integrated a function like this. I have to put a minus sign up front to account for the minus sign before m, which which will generate a spare factor of -1 in the chain rule. Now, alternatively, you can think of this as us performing a U sub, and this minus sign pops out of the U sub. So this is what you'd get if you set U to be 150 minus M. Great. Now what I'm going to do next is pretty much the same as I did in the last problem and the one before that. I will multiply by -1 first, reassign the constant so that I have log of 150 minus M equals minus T over 200 plus C. So C, I write C in place of minus C1. Then I will raise E to both sides of this equation and say, well, this is an equality between these two expressions. So this gives me that absolute value 150 minus M equals K, which has to be positive because it is E to the C, times E to the minus T over 200. And again, by the same argument as before, I can show that K actually can be so K can absorb the plus minus from opening up the absolute value, and so as a result I'll get that 150 minus M equals K, if I allow K to be both positive and negative, times E to the minus T over 200. And here, similarly to the previous examples, K can be a 0. So if we set K to be 0, then we get that M is constantly 150. M does not depend on T, it's independent of T, and it's just 150. And then such an M is going to be a solution of this equation here. So if we set M to be constant equal to 150, we have 0 both in the left-hand side, because we have derivative of the constant, and 0 in the right-hand side because it's 150 minus M. And so as a result, I have that M of T equals 150 minus K times E to the minus T over 200. And so this is the solution of our differential equation. Next step would be to use the initial condition. So we have seen that our initial condition is saying we had 20 kilograms of salt in the tank at T equals 0. Now, what this tells us is that I'm going to put M of 0. On the one hand, it is 20 by the initial condition. On the other hand, it is 150 minus K times E to the minus 0 over 200. So this is really just 1. And as a result, I get 150 minus K. And so this gives that K must be 130. And finally, the answer to my problem that takes the initial condition into account is that M of T equals 150 minus 130 times E to the minus T over 200. Now, it is instructive to study the behavior of this function again for T goes to infinity. So what happens after we let this tank run for a long time? So let's look into that. So what is the limit? Now, this is an additional question. We have already answered the question of the problem. We're just playing with it a little bit to see what else we can learn about it. And so the limit when T goes to infinity of this function is going to be the limit of expression I have here, which is, well, nothing, of course, happens to the constant. And here I have, again, exponential to a negative constant times t. So this here goes to 0 when t goes to infinity. It's exponential to minus t over 200. And my limit ends up being 150. So if we let the tank run for a long time, we have 150 kilograms. We're going to have 150 kilograms of salt dissolved in it. Now, this also makes sense. Well, first of all, a picture for it would be that we have a horizontal asymptote at 150. So our picture will look somewhat like this again. So if this is m of t, and this is the time axis, then this is m of t equals 150, and this is going to be the horizontal asymptote of our tank. And so over time, m of t approaches this value. Now, to go back to our in fact, this is slightly different because at the beginning we had not 0 kilograms but 20 kilograms, so this is slightly shifted like so. So here we have the initial condition, which is m of t was 20, and then from there it grows to 150. So this is what the curve will look like. Now, this picture and this quantity actually, this value here, 150, makes sense, in fact, because if we look back over here, we see that the brine has concentration of 3% of salt. So the mass of salt in the brine is at 3% of its total mass. Now, what happens to this system after we let it run for a long time is that the solution in the tank is equalized in terms of its concentration with the brine, and effectively everything in this tank is precisely brine. Now, since the brine has concentration at 3%, after we let the system run for a long time, we will also have concentration of 3% in the tank, and that means we have 5,000 liters total. That's roughly 5,000 kilograms of total mass, and if you multiply 5,000 by 3%, you get precisely 150 kilograms, as we see here. So what this is telling us is just that if you run the system for a long time, the concentration of salt in the tank will be equalized at the concentration of the brine that's flowing in. So that actually makes perfect sense. And so this is how you model mixing problems using differential equations. And the key here was to use this equation here, which used that the concentration of solution draining from the tank was the total mass of salt in the tank at the moment t divided by the total mass of the tank. So that gave us the concentration of the draining solution. And this is how you work with mixing problems.